Hello students, welcome to this module, which is part 3 in our series on basics of hydrodynamic stability, which is part of the course CHE 614 at IIT Kanpur. Basically what we are trying to understand is that suppose I have in the context of ordinary system of ordinary differential equations. Okay, suppose I have a system of linear ordinary differential equations of the following type, right? A is a matrix. It's a matrix with only constant coefficients. It has no x's, or the x is, let's say, an n-dimensional vector xn. Okay, matrix A is independent of xi's and time. Okay, now we all know how to solve this if I tell you what the initial condition is. For a specific initial condition, we know how to solve this. We can solve it numerically, or you can solve it using the method of eigenfunction expansions, wherein you say that if I know the eigenvalues and eigenvectors of the matrix A or the linear operator A, then I can expand x of t I is equal to 1 to n, okay, times ci at time t equal to 0 e to the lambda I t times vi, where ci is at time t equal to 0 or the expansions coefficients of this initial condition x naught, which is known or prescribed to us. I is 1 to n ci at time t equal to 0 times vi. Okay, so if you know this, you can find this coefficient of expansion using orthogonality of eigenfunctions, and then you can solve for the time evolution. Suppose the question we asked was, in the scenario of hydrodynamic stability, the initial conditions are not known precisely usually. So we are faced with a peculiar situation wherein we have a system of linearized differential equations and boundary conditions, but the initial conditions are not known. So how are you going to solve this problem? The same problem can be posed here also if we did not know the initial condition, right? If these were not known. If these were not known. Okay, if these were not known, then can we say anything about whether the system is going to, if I give a random initial condition which is not known to me, whether the system is going to stay close to that initial condition or it's going to be unstable? Now, even if the coefficients of expansion are not known, then I told you that we can look at the eigenvalues, and if even if one eigenvalue lambda I has I'm assuming lambda is to be real for simplicity, is greater than 0, then the system is unstable. The reason is because even if let's say lambda 1, lambda 2, so on up to lambda n, let's assume that lambda 1 is greater than 0 and all these are less than 0. Now, even then the system should be considered unstable, because any arbitrary or random initial condition x0 will, when you expand this, will have c1 v1 cn will have this component c1 not 0. If this component c1 is not 0, the corresponding eigenvalue is positive, lambda 1 is greater than 0, therefore things are going to grow exponentially in time. Now you may argue that, suppose what if my initial condition, a special initial condition where x0 does not have c1, because you may think of an initial condition where you start with c2 plus cn vn. in this case, because only lambda 1 is greater than 0, the time evolution of this superposition will be stable in general if the eigenvectors are orthogonal and so on. But the point is, this is a special initial condition. This is not an arbitrary initial condition. What we are interested in is stability or instability with respect to arbitrary or random initial conditions. Therefore, even if one of the eigenvalues is positive and all the others are negative, we should consider the system to be unstable. And if all eigenvalues are such that lambda is less than 0, then only you can consider it to be stable. But this stability is also, I told you, is only in the asymptotic sense, because if I plot let's say some disturbances as a function of time, right? The fact that things are decaying exponentially means that sufficiently large time, t going to infinity, things are going to decay exponentially. But this doesn't guarantee that it is a monotonic decay. If the eigenvectors vi's are not orthogonal, okay, then the superposition of eigenfunctions and those exponentials, this superposition, even though all the lambda i's are less than 0, yet there is a possibility that at early times, because the eigenvectors are not orthogonal, there can be a growth and then eventual decay. Okay, such a growth is called a transient. So this is time versus amplitude. This is called a transient because it's only transient, it's not permanent. Again, it grows. This is called transient growth or non-normal growth, because it comes from the fact that the eigenvectors are not orthogonal or orthonormal, or it is also called as algebraic growth because it is not exponential. This growth cannot be e to the t or something times t. It can be of the type t to the alpha, where alpha can be half or something like that, or t squared. Alpha can be half, 2 or 3 or whatever, right? Now, this is in the context of ODEs. Now let's go back to the combined Couette-Poiseuille flow problem. Stability of that. We had derived the linearized evolution equations a couple of modules before. So here, if you remember the setup, you had the flow is two-dimensional, and this was x, y inside the board or the plane of the screen, z is perpendicular to the wall, and this is the flow, okay, along the x direction. And these are the two walls, y is equal to 0, sorry, z is equal to 0, and z is equal to b. And this is the laminar flow velocity profile, u as a function of z, whose stability is considered here. Now, again, in the same spirit as this problem, solving using expansion of the unknown in terms of the eigenvalues and eigenvectors or eigenvectors, here I'm going to do an eigenfunction expansion. Okay, first briefly recall that if you have an infinitely long domain in the x direction, then we use what is called the Fourier transform that I introduced a couple of a few modules ago. So here we say that the function f of x is written as integral over dk f of k, f tilde of k, e to the ikx dx, and this is called the Fourier transform of f of x. Okay, k is continuous, a real continuous variable. Okay, so whenever the x domain is infinite, we use a Fourier transform. Here we have to look at, there are three coordinate directions, x, y and z. X is infinite, right, because we are assuming the channel to be an infinite channel. We'll also assume y to be infinite, because we are assuming two-dimensional flow. That means the side walls are so that means that the distance between the two plates is so small compared to the width of the channel. We are going to effectively assume y also to be infinite. So along these two directions you will have Fourier transform. Along the z direction, it's a confined direction, you will have an eigenfunction expansion. It's a summation, whereas here these are all integrals like the ones I have shown. So what I'll do is I'll first write down, okay. So remember that in the previous module on linearizing the Navier-Stokes equation, I told you that you write Vx as Vx bar plus Vx prime, etc. So we are going to write an expression or an eigenfunction expansion for this particular variable or any general variable. Let's call it a, the perturbation variable, x, y, z, t is nothing but, let me first write this. Let me write here from here, summation n is equal to 1 to infinity. This is the discrete sum for the eigenfunction expansion along the z direction. Integral minus infinity to plus infinity dkx. This is the Fourier integral along the x direction. This is the Fourier integral along the y direction into the plane of the screen, okay, times. Now I'm going to draw an analogy with what we had here, okay. Let me just copy this part here. Okay, this is for the discrete case of ODEs we just recall. Okay, now there are coefficients which are time dependent, which are finally satisfied with respect to, these are in general some time dependent, these are some coefficients, okay. So you can combine these two to form some ck as a function of time times ci rather. Vi, okay. Now in the same way I'll have coefficients. Let's call these coefficients b and k, t, n. Okay. Now the reason why it's a function of k is that k is a real valued variable, so it will become like a smoothly varying continuous a function of k, and n is basically the summation along. In principle I should write it as it's a function of kx, ky time, okay. And what I will do also is that now I will write the eigenfunction in terms of the z direction. These are discrete values, these are numbered with n, but they will also be functions of k, and they are functions of z, okay. And finally you will have exponential of I kx times x plus ky times y. Here kx and ky are called the wave numbers in the x and z y directions, okay. So this is exactly what we have. The next thing we can do is the time dependence has to be exponential, in the same way as we guess the time dependence to be exponential for the matrix problem. So this I can write it as sum b cap or b tilde of n of kx ky times e to the st, okay. So and you can think of this as a Laplace transform into of the time domain into the S domain as well, if you want to think of it like that. Okay, then this will be a function of S. Okay, and so finally, this is the way we expand our unknown disturbance variable, let's say A, which can be any of the velocities or pressure disturbances, in terms of the eigenfunctions along the various coordinate directions. Along the x and y directions, they are infinite directions, so you use Fourier transform with wave numbers kx and ky. Along the other direction, the z direction, it is confined, so we don't know what these eigenfunctions are. Okay, so we have to solve for them. Now, in the same spirit as what we used for the previous case, that is, instead of, because we do not have a precise knowledge of the boundary condition, out here also remember that I just wrote this as Ci at time t equal to 0, e to the lambda I t vi. I took a typical term and then substituted this back in the matrix problem. In the same way, I will take a typical term. I am not going to solve the initial value problem. In the method of normal modes, we take a typical term of such an eigenfunction expansion. So we'll say A of x, y, z, t goes as phi n of z. We will keep the this is actually kx, ky. Actually, we'll keep this. We'll omit this dependence for the sake of simplicity, and then we'll write e to the I k x x, e to the I k y y, e to the st. Okay, and this is the method of normal modes, and s is the eigenvalue. If real part of s is written as sr plus I si. Okay, s is called the growth rate. This is the eigenvalue in our problem. S is sr plus si. If sr is greater than 0, the flow is unstable because things are going to grow exponentially in time. If si is less than 0, the flow is asymptotically stable. Okay, so this is the method of normal modes. We substitute this back in the set of 3 PDEs or 4 PDEs. Now, because the functional forms along the x, y, and t directions are exponentials, then the derivatives along those directions will simply vanish, because you can easily take the derivatives of exponentials, as I will show in due course. And finally, you will end up with a ordinary differential equation for phi n of z, and it will be a fairly involved ordinary differential equation, but yet it is much simpler than solving 4 coupled partial differential equations. And this will be an eigenvalue problem, because only for some special values of s will you get non-trivial solutions. So we'll see how that is done as we go along. Right now, we should understand very clearly that in all initial attempts of understanding a stability problem, we do not solve the initial value problem. Instead, because we do not know what the initial conditions are, it's a very practical issue. Instead, we solve the eigenvalue problem. This is called the method of normal modes. And the stability that we get out of this is called asymptotic stability, because it's valid only as t goes to infinity. Okay, therefore this eigenvalue approach will not tell you whether there is transient growth and eventual decay. If all the modes are stable, okay, this cannot be predicted using the this transient growth cannot be predicted using the eigenvalue approach. You need the superposition. so of all the eigenfunctions to predict eigenfunctions or eigenvectors to predict transient growth. Okay, and I'll stop at this point. I'll try to illustrate this idea of a normal mode analysis using a simple toy problem in hydrodynamic stability in the next module. Thank you.